easy. Just
By definition. Yeah, also and then thermodynamics.
Isn't like the cosmos or
I thought they'd be more together.
like the cosmos or I mean,
Within thermodynamics is hard enough, like that's.
I mean, like with actual gas of actual stuff.
yeah. All right. So right now it is on YouTube.
Yeah.
The mathematical. I'm trying to remember like the.
So should we start or should we wait for a bit more minutes? What about you guys? Or yeah, everyone grab a piece of pizza.
Guys, how do I click on anything?
Uh-huh.
Like, you want to go to the next
Oh
slide?
yeah, it's right here.
Okay.
Yeah.
Yeah, partition function with respect to all.
Yeah, grab some. So let's start. Hello everyone. So we are having Xiaozhen Fu today, who's a grad student of Daniel Gottesman doing research in quantum error correction, to give us a talk on the brief introduction of quantum error correction and all related stuffs. So let's welcome Xiaozhen. Yeah, take over.
Hi everyone, I'm Xiaozhen. So today I'll be giving like a talk on quantum error correction. So feel free to grab some pizzas, enjoy the pizza. At least you'll gain something from pizza and if not from my talk. Okay. So before I start with this talk, I have to make an advertisement. So like we have this quantum error correction study group where like, so if you think you enjoy the talk and you enjoy the topic on quantum error correction, like feel free to contact me or Shubham to be added to the group. And like in this like quantum error correction group, we will basically be studying a wide range of topics related to this field. Yeah. So let's begin. So so first of all, like what is error correction? So error correction is like this way of ensuring like our communication is secure. So when you transmit information, for example, a long time ago, we have these hierographs and this Caesar cipher. These are ways to transmit information, but as you can see, it's not really efficient, and sometimes the meaning of the message can be lost. So nowadays we have like much better ways of transmitting information and also like ways to ensure that even if some errors occurred in our message that we are trying to transmit, there are many ways to correct for these errors. So for example, in 5G wireless communication, we have like some codes. They are using polar codes to correct for errors. And but this error correction is also used when you try to like encrypt a message. Then like when this encrypted message is being like attacked by malicious attackers, you can like figure out where are the errors, account for these errors, and successfully decode the message. Okay, so that's the whole idea of classical error correction. But of course, now we know that classical error correction is not enough because we have quantum computer. And you know, in quantum computer, things get a lot noisier. For example, if you are looking at some kind of experimental implementation of like a quantum computer, for example, using superconducting qubits or using some quantum optics, like using photons as a ways of transmitting information, then there's lots of noises and lots of things that can happen as you try to pass photons through like a quantum chamber. So for example, first of all, like photons might just fail to be emitted, or like your photo detectors fails to receive the photons, or like there's something wrong in the machine, or the photons interact with the environment and decouples. That's why we need quantum error correction. Yeah. So, so the way it works is kind of similar to the way classical error correction works. So for example, you try to encode a message 0 into 000. Then in this case, while transmitting, if some errors occurred on like one of the qubits. So think of these zeros as like the logic, computation in the computational basis of like qubits. Then like maybe if one error occur on one of the bits, you can still recover the message. because you can just take the majority and that will be the correct message, right? So it's kind of similar in the case for quantum error correction. So the idea is you have like a system of interest. So this system of interest is the information that you want to encode, and you place this system of interest into a larger system, consists of like way more physical qubits. So logical qubits, which is smaller, into like bigger physical qubits. And so the state of these physical qubits is such that it is a +1 eigenstate of an abelian subgroup of the polygroup. So first of all, what is a polygroup? So they are basically polys, X, Y, Z, and I. So they can be tensor products of these polys. Now we have we basically choose an abelian subgroup and make sure that these physical states of the system, of the large system, are the +1 eigenstates of all the poly operators inside this stabilizer group. Yeah, so this stabilizer group has like R generators. So each generator will reduce the degree of freedom by half. Okay, so for example, if you have n physical qubits, then if you have one generator, so then the degree of freedom will become like n-1, 2 to the power of n-1. So it's reduced by half. So you have like R generators, then the number of like logical qubits that you encode in the large system will be given by 2 to the power of n-R. Yeah. So for example, like one classic example is the 9-qubit code. So the 9-qubit code basically encodes one logical qubit into a bunch of, into 9 physical qubits. So this is the way it is encoded. And one of the stabilizers is given by Z tensor bunch of i's. So the way it corrects for errors is that, for instance, if there's a bit flip on one of the first two qubits, so for example, instead of 0, 0 plus 1, 1, you get something like 0, 1 plus 1, 0. And then if you look at the stabilizer, this stabilizer, one of these, you can see that it is no longer the +1 eigenstate. Rather, it becomes the -1 eigenstate. So so by just making these measurements using these stabilizers, you can check whether it is still inside the code space. Yeah.
So are there codes that aren't stabilizer codes?
Yeah, there are definitely like non-stabilizer codes. So that is actually outside this range of this discussion. So stabilizer formalism is nice because basically you're restricting the errors to like poly errors and give a nice set of formalism that people can work with.
What's a generator?
So generator for a subgroup, basically if you have R generators, then the number of elements in the subgroup will be 2 to the power of R. Right, so like basically you take like any of the generators, multiply them, you get the element inside the group. So these generators generate that subgroup.
So it's one of the M. In S, it's in S.
So M is just any element in the S, but like if all the elements in S like are such that the phi is an eigenvector, then basically you can just look at the generators and say that phi is a +1 eigenstate of the generators. That's equivalent.
So the way it was defined to me is it's analogous to a basis for a vector space, where like you can make any vector by adding together the basis guys, and you can make any element of the group by multiplying together the.
I'm trying to see how that leads to, so you have n qubits and two state systems.
Yeah.
You have R generators. Like, so a generator is
The
is
generator
X, Y, like II, is it?
Each of the generators are in the poly group. So it's something like
This is like a product?
tensor products of X, Y, Z, or I. Yeah.
It's a tensor product, not product. So like ZZI means the first two Z is acting, the first Z is acting on the first qubit, the second Z is acting on the second. And we do nothing to the rest of the qubits.
Yeah. Also, like every time you have include one more generator inside the stabilizer group, you basically like create more correlations between the physical qubits. So you are reducing the like degree of freedoms of the physical system.
You like connect the qubits.
Yeah, you're like entangling the qubits. Because like, for example, if you perform like measurements X on 4 qubits, you're like entangling these 4 qubits into like the eigenstates of the measurements that you're performing. Yeah. So let's look at like one example of how like stabilizer formalism is used to encode one logical qubit into a 2-dimensional lattice. So in this diagram, we have like a bunch of qubits represented by the white dots and the black dots. So these black dots are ancillar qubits. The white dots are the physical qubits. So for example, this black dot basically measures these 3 white qubits in like using in the basis XXX. So it basically projects these 3 qubits into +1 or -1 eigenstates of XXX. Yeah, so if you count the number of stabilizers, basically count the number of like yellow crosses and green crosses, there are like a total of n-1/2 X stabilizers, n-1/2 Z stabilizers, and there are a total of like I think around so if you count for this one, actually if you just check, you can see that there will be a total of like 1 logical qubits. Yeah. So basically take the total number of like physical qubits there minus the number of X and Z stabilizers, and they give you the logical qubits.
Wait, so you're saying there's only 1 logical qubit for this?
Yes.
Yeah. Yeah. So
So this is very low efficient.
yes. Yeah. But like it is good because it protects this logical qubit against any like local errors. So if you locally perturb like any of like a small number of like physical qubits, it doesn't like destroy the information of the logical qubit that you encode into the system. Basically, like the long range entanglement of this large system like helps to fight against like decoherence from the environment. So it gives it like good error correcting properties.
Can you give us like a brief definition on how the logical qubits of surface code is defined? Like is it defined by the majority rule, or is it defined by some chain number, etc.? Or yeah, like when is it 0, when is it 1?
Okay, so I guess I can answer your question in the next slide. So so once we have encoded one logical qubit, the way logical operation is performed is by defining these X and Z logical operations. So X logical operation is done by just applying X polys in a string, and Z logical operation is done by applying Z's in a string. So if we do that, then actually we can use this method to like prepare our like logical qubit in like a eigenstate of like Z logical or X logical, and that will give us like a method for state preparation. Yeah.
So you're saying that to see the logical qubits, we have to multiply by all the operators together on a line or something like that, or to get some to get their eigenvalues, or no?
Okay, so wait, so what's the question again?
So my question is like, how do we define the logical qubits? Like, what defines the 1 or -1 in the surface code?
Okay, so for example, like so for example, you do the measurements and like all this is like in the +1 eigenstate. So you have encoded logical qubit in the +1 eigenstates of all these stabilizers. And then like it is now in the code space, but you're not sure like what exactly is the state, right? So if you want to prepare it in like a specific state, for example, like for example 0, right? So that will be like a logical eigenstate of the 0 logical operation. Yeah, then I think there's a way of measuring the qubits over here. So if you prepare these states, I think in the 0 in the 0 state, then you perform the measurements. Overall, you will get like a cat 0. But I think you have to double check the state preparation details.
Okay, okay.
Yeah.
What do the like the X and Z correspond to sense in like in the laboratory? Physically, what?
So well, actually, so these X and Z polys, they are not performed on the hardware. Yeah.
What does it represent?
So for example, if this is in a computational basis 0, then if you apply X, it just become a 1, right?
How do you apply that?
So it's actually applied, it like experimentally is done on classical computer. So this, you can commute it through a like quantum circuit and then apply at the end before your measurements. So there's no need to like perform it on the hardware. So the only thing that is performed experimentally are the measurements themselves.
So
which are,
what are you measuring here? What would be the measurement?
so the measurements here are all the like stabilizer generators, which are the X measurements and the Z measurements.
Like use polarized light.
Yeah, I guess it would depend on your experimental system, which are,
Like if these were a bunch of spin halves, say.
yeah, then the +1 or -1 state would correspond to 0 or 1 state.
So I think what I'm actually not sure how it's like done.
Measurements and measure the NCR. Use the NCR to correct the parity information and then measure the NCR to figure out where the state is in the possible state.
Yeah, but exactly how these qubits are like prepared, like we can use different kinds of systems. So for example, you can use like superconducting qubits, or like you can use trap ions, prepare a 2-level system. Like the physical realization will like not really be discussed here. Right, so like once you set up one logical qubit, it's possible to create more like logical qubits by removing one stabilizer generator. So if we do that, we basically increase the number of degrees of freedom by 1. So there's one more logical qubit. And we can define the X logical and Z logical operation corresponding to this extra logical qubit. Yeah. Then using the same method, we can create like 2 extra like qubits. So now on this surface code, there are a total of like 3 logical qubits. This is like basically done by increasing the degree of freedom on the surface code by removing some of the measurements.
What prevents you from just making like an arbitrarily large number of logical qubits by just taking out stabilizers?
Right.
Yeah.
So there's actually one problem we face here. So it has to do with like the number of errors that you can correct. So previously, when we look at the X and Z logical operators, you can see that it spans across the entire lattice. So you need like, so you can correct for like errors that is proportional to the length of the lattice. So in this case, unless like 3 or more errors occur, like for example, if you look at this string, so if like the error x1, x2, x3 occur, then when you are correcting for it, you might think that only x4 and x5 are the errors, and so you apply x4 and x5, and then the overall effect is that you create a undetectable logical error of like applying a logical x on your like qubit without you knowing. So so when you have like a smaller string, it's actually meaning that the number of errors you can detect or correct is less.
If there are two errors on a single string, you cannot correct. You don't know if it happened.
Well, so the way like people do this check for errors. So for example, like if for example, okay, I should explain this. So for example, if a Z error occur on this qubit, then if you do a measurement, then this measurement will give like a different output. So suppose it's supposed to give +1. Because of this Z error, it anti-commutes with X and it gives -1, right? So, but from this measurement, you can only tell that there is an error occurring in one of these 4 qubits. So if you look at the measurement outcomes of all these measurements, you have a bunch of +1s and -1s, and basically you try to figure out like where exactly did the errors occur. And that is, I think, done using percolation theory. So before you actually run this surface code, you check like where the errors occur and what are the corresponding outcomes to these errors. And then, so you do like a mapping, but this mapping is not necessarily one-to-one, because if there's more errors that occur than what you can correct or detect for, then like when you're trying to correct for the errors, you might accidentally just mess it up. Yeah. So for example, if like a Z error occur here and a Z error occur here, so this will not give, this will not tell you that errors occur, but the ends of this pair of Z errors, which is this and this, will give a -1.
So if it's a string of error, you cannot detect.
So if it's a string of error, like the boundaries of the string will give you a -1 outcome. And from there, you can tell that these 2 errors are like correlated. Yeah.
Yeah, because the excitation is modular too. Like you can only create 2 excitation or initial 2 excitation. So that's fine.
What is an error? What does it mean for an error to occur?
So well, that just means that like there's X, Y, or Z polys occurring on one of the qubits. So of course, like if you think of errors, it could be like it is actually continuous, right? Like you can have like a small error occurring. For example, you can map like the state to like 1 plus epsilon times X acting on the error. I mean, acting on the state, right? But like these measurements will either project it back to itself or project it to something with a poly acting on a state.
So you have some kind of specified state in mind. Is that an error is a departure from this state?
Sorry.
That like you have some kind of configuration of the qubits in mind, and this error is a departure from that configuration?
Yeah, exactly.
Okay.
So remember when we talk about like the stabilizer group? So anything that any code word is basically a state that is a +1 eigenstate of all the stabilizers. So if your state is like a -1 eigenstate of some of the generators, that means that it is now not in the code word. Like somehow one of the code word has been like moved to some error space due to an error that occurred on the state. Yeah. Right. So right. So just now I was saying that you can create like two extra logical qubits by turning off 2 measurements. And you can define the corresponding X and Z logical operations for these 2 logical qubits. Then the way people like do is that they just throw away 1 degree of freedom and consider this as like a single logical qubit with a single pair of X and Z logical operations. So the X logical operation is just a string connecting them, and the Z logical operator is this loop here. So a nice thing about this is that now you can actually move them around. And then you can like move them in a circle, just kind of nice. So the weird thing that happened is that when you have two such pairs and you try to move one loop, one hole around the other hole, it actually creates some like interesting overall action. So you can think of this, each of them has representing one logical qubit. Now, if you move like one hole all the way around another hole, in this case, it actually doesn't do anything. But like, as you can see here, so this, it also doesn't do anything. When you apply like X logical operator and move this hole around the other hole, like the braiding creates this overall effect of X tensor X. So what we have done is that from X tensor I, by moving one hole around the other hole, you create the overall effect of X tensor X. And if you have like I tensor Z and you move one hole around the other, the overall effect is a Z tensor Z. So overall, this means that if you try to braid like two qubits, you can actually implement a logical C0 on a surface code.
So, I mean, how are you, I guess it like retains, is this like a dynamical process? You're going around, you know, one hole going around the other?
Yeah.
So it has to have some kind of, I guess, memory of where it was. Is that true?
So I guess if you try to move it down, right? For instance, by moving the hole down, the way it is done is like you have to switch off the measurement here and then turn on the measurement here. And if you keep track of your measurement outcomes, you can still like, you can know like what are the syndromes of the measurements, and you can determine like whether there are errors occurring. So you can still keep track of the errors and keep track of the state that is being encoded. I guess there's a lot of like details here, but you don't really have to like.
So it's braiding, it's a dynamical process?
What do you mean by a dynamical process?
In time, I guess, you know, it has like
yeah, in time,
okay.
yeah. Yeah, you're moving in time, like, yeah. So just an aside, this braiding is also done in like a color code, which is another kind of quantum topological quantum error correction code. So what we saw just now is that for surface code, we can implement like different kinds of gates, like X, Z, C0, and we can also implement some Hadamard gates pretty easily and fault tolerantly on surface code. The question is like the kind of gates that you can implement on this code. Does it form a universal gate set? And the answer is actually, if you want to have a universal gate set, like it has to be a set that you can use to like in a finite sequence to approximate any like unitary operator you want. But like, unfortunately, you need like Clifford gate plus some gates that's outside Clifford gates in order to form a universal gate set. So actually for surface code, we don't have like a set of like gates that's both universal and fault tolerant. So it actually requires some other method, which is called magic stick distillation, which I will not talk about here.
So what does the efficient mean here?
Right. So I think what Solovay-Kitao theorem says is that like this finite sequence of gates can like obtain a set of unitary operators that are dense inside the whole set of SU2 space.
Yeah, is it like a polynomial time, or is it like exponential time or logarithm time? Or?
I think it's around polynomial. It's not exponential, but you can
yeah.
check.
So does the theorem clearly states that it's done within polynomial?
Yeah, it does
okay,
state
yeah.
that.
Gotcha.
It's just like a unique, are there, you know, like, so universal gate set, should you have, is it unique? Are there
It's
multiple
not
universal?
unique.
Okay, and
Yeah.
do they all scale, you know, with polynomial?
I think the answer is yes, like according to this theorem. I actually need to double check and read this again. Yeah. Right. So I guess the idea that I'm trying to bring across here is that like it's probably easy to have a universal gate set because like this gate set is finite. But the problem is that you still want to implement these gates fault tolerantly, which means that like it doesn't spread errors like uncontrollably when you implement that gate. So one of the techniques that people do is like to use this transversal gate. But there's this, and transversal gates are fault tolerant. However, like according to a 2008 paper, these transversal gates, they can never implement a universal gate set, no matter what quantum error correcting code you use, right? So what is a transversal gate? Now, the idea is that if you have a non-transversal gate, for example, like you just implement like C0, then if you start off with one error on a single qubit, by the end of your computation, you have like Z errors on 3 qubits. However, if suppose like only transversal gates are used, say for example, in this case, then if a Z error occurred on one of the qubits, the unitary operation that you apply only acts on the single qubit. So the errors do not spread to the other qubits. So there's like limited error propagation. So we consider this kind of gates to be fault tolerant. So so by extension, like transversal gates are fault tolerant.
Are there any transversal gates besides swap and single site gates?
Yeah, there are definitely. I mean, so like by the definition of transversal gates, basically any like unitary operations that can be written as product, like tensor products of unitaries, each acting on a single qubit.
Yeah,
is
sure.
transversal.
Products of swaps. Is there anything else?
It's not just swaps, it's unitary.
Okay.
Yeah, so any like tensor products of unitaries, right? If you can implement this unitary action as a gate, then I guess that will also be transversal. So, but that is not the only technique to have fault tolerant gates. Yeah. Right. I think I'll skip this. And then over the years, there have been a bunch of like no-go theorems that people have proved for topological stabilizer codes on the kind of gates that can be performed, as well as like distance bound. So like I said earlier, so surface code, so we were talking about surface code earlier on. So it's actually also a topological stabilizer code. So by that, I mean that like these X and Z stabilizer generators, they only involve like qubits that are like local to each of the generators. And each generator can be placed inside like a hypercube of a constant radius. Right. Yep. Okay. So there are a bunch of like theorems, and actually most of them are not too hard. Like they mostly make use of this cleaning lemma, which is actually pretty interesting. So it just says that suppose we have like a topological stabilizer code. So think like a surface code. And now, so these black and orange dots are the qubits. So we consider a logical poly operator. So that involves applying polys on some of the physical qubits, right? And so if we know that in this region M doesn't support any like poly logical operators, then we can clean M of any of the logical poly operations. Yeah, so So first of all, we know that like there's an equivalence class of like logical Pauli operators, right? Because if P is a logical Pauli operator, then P multiplied by any elements from the stabilizer set gives us an equivalent logical Pauli. So like basically this is saying that if M doesn't fully support, then we can find an S such that P multiplied by S gives like Paulis only acting on qubits that are outside the blue region.
What does the clean mean?
Oh.
What does cleaning mean here?
Well, it just means that you can find such a S such as P dot S only acts as identity on M. Yeah.
Okay.
Right.
So are these dots acting on something in a state, or
So these dots are the qubits.
the dots are the qubits?
Yeah. So we are looking at the set of qubits.
So I recall earlier, so like you have M on the psi equals psi, right?
Yeah.
For all the M and
S, that's
and
right.
S.
Yeah.
So so M is kind of like an operator, right? Is that correct?
Right. Okay. Actually, there might be a mistake on my part. So here I'm just redefining M as this region. I'm just calling this region as M. So this region which consists of these qubits, yeah, I'm just labeling this region as M. Yeah.
But there can be Paulis between M and out of them.
Yeah. So I'm not really sure what you mean. So you can, so basically like these black and orange dots are just qubits, and you can like, so these qubits are placed on some lattice, right? And then I'm looking at like one sub-region, one subset of the qubits, and I'm saying that if like there's a quantum error correcting code on this whole set of qubits, and now I want to apply a logical Pauli operator. So for example, for surface code, if you want to apply a logical X operator, it will be the string of X on a bunch of physical qubits. And I'm saying that like if like this region M, like you cannot find any like logical Pauli operators that only act on M, then I can do some cleaning and remove like the Paulis that are acting on the qubits inside them.
So the orange means Pauli matrix acting on a qubit.
Right. Yeah. So this orange means that there are some Paulis acting on. If it's black, that means it's identity. Yeah. Right. And okay, so
And sorry, can you go back to that slide? So in order for you to not be able to do that, everything inside of M would have to have been acted by a logical operator, right? That forbids you from cleaning out that region M.
actually, that's not what the lemma is saying. So if you can find a logical operator that is like fully supported on M, so like you choose a logical, so there exists a logical operator such that it only involves Paulis acting on qubits inside M, then like one cannot clean M from having Paulis. That doesn't make sense. Yeah. So like the idea is really that you can clean a region as long as it doesn't fully support the logical operator. And so this cleaning lemma is used to prove an upper bound on distance on topological stabilizer code. So in particular for 2D, it is saying that for any 2D topological stabilizer code, if you have a logical operator, they will definitely look like a string. So it basically involves a bunch of Paulis that has a dimension that is that makes it look like a string. Yeah. So if you visualize the surface code, the X logical operator also looks like a string in that case. Basically, the width is finite of constant size, but the length is proportional to the size of the lattice. So, and the idea is that you can use a cleaning lemma to clean the blue region so that any logical polys is only supported on the green regions. And then from there, you can actually like work it out and conclude that any logical polys is only supported on one of the strips. And that means that it must have a constant width, and its length can be proportional to the length of the to the dimension of the lattice.
So good question here. So here you are basically defining the sort of topological space in terms of poly operators, right? Or the so-called topological space.
So if you go back, okay, so the way I define topological stabilizers code is well, it's basically the qubits are like residing in a d-dimensional lattice, and if you have a stabilizer generator, it can be confined to like a hypercube of constant length. So I'm not making any statements about the kind of like stabilizer generators.
Then what's non-topological in your definition?
For example, you can have for example, like you can have like one example is the Rick-Muller code. It's a 15 qubit Rick-Muller code. So for that, like the stabilizers actually involves qubits that are like far apart, and you cannot place the qubits into like a 3-dimensional lattice. It's basically a non-local code. But in this case, it has to be local, and for the stabilizer generators.
So it's a little bit different from like the long-range entanglement or topological order.
So should that be like the number of logical qubit depends on the manifold?
Yeah,
Because rhetorical, you will have Z plus Z2, that means you have 2 logical qubits. And if you have surface code, then you only have 1 logical qubit.
Yeah, definitely. Like the number of like logical qubits inside like on a certain manifold depends on like the boundaries, the number of holes, the genus of the kind of boundaries, whether it's rough or smooth boundaries. So it does like the number of uncoded logical qubits also depends on the topology of the system. Right. And
could you go to the page? I think I'm losing the big picture. Why do you want to clean some stripes of the 2D code?
Right. So we are like proving an upper bound on the distance of the logical operator on a 2D code. So for instance, so you know that the distance is the minimum, is actually defined as the minimum weight of all the logical operators. So if you show an upper bound on distance, you are showing the like lower bound on the weight of logical operator. And then it has like results on whether one can achieve a self-correcting quantum memory for 2-dimensional topological stabilizer codes. So the statement that I'm going to make here is that because for 2D, the logical operators are string-like, so you can actually show that like whenever there are some errors occurring, like so the anti-communication only occurs, like the measurements that give -1 only occurs at the end of a string, right? And so the energy barrier. So if you can like treat the stabilizer code as like a Hamiltonian, I mean that's like a bunch of details that I don't know. I didn't really prepare to explain. So
so it costs 0 energy to separate the 2 defects to far away. That is what
yeah, you can think of it as the activation energy to go from one code word to another code word is constant. But in order for it to have like a self-correcting quantum memory, you need to have like a large energy barrier, right? So this large energy barrier only comes from these anti-communications at the end of like a logical, at the end of a string of errors, right? If a string of errors is only like string-like, then that means that you can't really have this large energy barrier.
So you're saying that the system has to be gapped, like if we have to prepare like a system as quantum memory, right?
Yeah, and the gap has to be large
Very large.
enough,
Okay.
right?
And
I mean, like it is always gapped, but it's not just gapped, right? Because we are looking at a degenerate like ground state of a Hamiltonian,
Yeah.
right? So all the coverts are the ground state of this Hamiltonian. But like going from one ground state to another ground state, it has to overcome this energy barrier. That has to be large enough.
Oh, that's weird. So if we prepare a system like that, then what does the spectrum look like? Like we have like a bunch of degenerate ground states. So you're saying that if we perturb it, then the energy splitting is large, right? Is that what you mean?
Okay, so if you want to know more about this self-correcting quantum memory, please attend tomorrow's Alexis group meeting, because there will be a person who will be presenting on like achieving quantum memory on a two-dimensional.
Okay, okay.
So here, the ground state degeneracy is coupled to the genus of the surface. Right? So it is natural for
I'm actually really
different
tired, so I'm losing track. Can you say it again?
So the ground state degeneracy
Uh-huh.
is proportional to the genus of the surface. Is that right?
No, not just on the genus. Like I mean, it depends on a bunch of things, right? Like it depends on topology. Like if you change like the boundaries from rough to smooth, or like you increase on, yeah, it also depends on the genus. That's right.
Use
Also.
the number of holes, right?
Yeah, the number. If you have more number of holes,
Yeah,
then
I mean, there's this equation on how like logical qubits depends on like these things. It also depends
yeah,
on
there are
the
two kinds of boundaries: rough and like
yeah.
trivial C and trivial X.
It
So
also
how
depends
about,
on orientability of the surface.
Okay.
Why would it depend on the genus? So is that like where I'm thinking of like a previous figure where you took some out? I use the holes that we're talking about. Like the defects, I think you referred to earlier, the defects where there was like a removed qubit.
Yeah, I think yeah.
Does this correspond to the genus?
The number of logical qubits you have depends on your genus. So for a planar code, I think it's like twice the number of genus is the number of logical qubits you have.
So it depends on the homology group, actually, like the dimension of the homology.
Taiwan.
So if you have a torus, like I think if you can look at the homology and like from there deduce the number of logical qubits. So it's,
So is the, I guess, are we referring to the qubits earlier?
well,
Like what space are we talking about? What, like, we're talking about topology, right? So the topology of what space?
Lattice.
lattice.
Oh, the lattice. So
Yeah.
the genus would be the number of defects.
No, genus is not the same as the number of defects
Mm.
there. So the genus there is always 0. Like we are just doing it on a flat surface. But like, for example, if you look at torus, then that has genus equals to 1. Yeah.
So the energy barrier crossing different topological sectors is actually proportional to the system. So it costs infinitely by energy, thermodynamic limit.
Yeah, I guess
Really?
for 3 dimension, you can have like logical operators that are like 2 dimension. Then
So
in that case,
yeah, it's always codimension 1 defect. That is.
yeah, that's what I understand from this paper.
But already for two dimension, it costs infinite energy to cross different topological sectors of the ground state, right?
No,
Or-
for 2-dimensional, like the energy barrier is constant.
It's constant.
Yeah. I mean, only in the case where like the stabilizer codes are like topological stabilizer codes. We're not talking about other kinds of error correcting codes here.
How does it scale with the system size for the other dimensions? Say it's constant for two dimensions, about 3 and 1.
What skill says?
Oh, I'm sorry. So how does it scale with not system size, but like
What skill says system size?
The energy.
yeah, right.
The energy vary between topological sectors.
So for example, for 2D, it doesn't really scale with system size. That's like based on the results of this paper. But if you look at higher dimension, it could scale as like the width of a logical operator. So we can expect it to like increase linearly with like one length of a lattice. I think we are almost out of time.
We're good. You have
All right, so
more time. Yeah.
oh yeah, okay. All right, so I'll just go through. This is the last result in this presentation, the Bravik-Koenig theorem, in a paper from 2012. So the question that they are trying to ask is, given a constant depth quantum circuit, what kinds of quantum gates can we obtain for any topological stabilizer code? So the reason why people are interested in these constant depth circuits is that like these are another technique for implementing like fault tolerant gates. So for anything that is constant depth, like if each gate is only involved like R qubits, and if like you only have a depth of H, for instance, then the total number of qubits then can be affected is at most like R times H. So because like the way like errors can spread, like from 1 qubit, it can only spread to a constant number of qubits. So we say that this is also like fault tolerant because errors propagation is not uncontrolled. Yeah, so people study like given using this constant depth circuit, like what kind of gates can they implement? So the kind of gates that people are looking at is whether it is a Clifford gate or a non-Clifford gate. A Clifford gate is something like a Hadamard, CNOT, or phase shift. And a non-Clifford gate is something like a pi/8 gate. So for example, for surface code, you can only implement like Clifford gate fault tolerantly, but not non-Clifford gates. So these non-Clifford gates are actually implemented through like other ways, like such as magic state distillation. So what people have found is that for this theorem, it basically says that given a d-dimensional topological stabilizer code, the gates that you can implement are at most of like the div level Clifford hierarchy. So only when you go to like 3 dimension, we will start to see like non-Clifford gates implemented fault tolerantly. So here I was actually trying to show you why is it that for surface code you just cannot find like constant depth circuit implementing non-Clifford gate. And I guess I'll just skip the proof for now. So if you're interested, you can go back to the slides. Yeah, and for the general case for d dimension, the proof actually just make use of the lemma that we went through earlier using the cleaning lemma. Yeah, so that's all.
Yeah. All right, thank you. So any more questions for Xiaozhen on any kind of topics?
Why is it called surface code?
Because it's on the surface.
Yeah. Any more questions?
If you are interested in like learning more about surface code or any other quantum error correction, like please feel free to contact Shubham and he'll add you to a quantum error correcting group where we do this like weekly meeting to present something more in details.
So you guys like group theory and
Yeah.
Right, no questions. Let's thank Xiaozhen again. Thanks for the nice talk.
Seems like a really nice field where you can, I was thinking like, can you implement like group theory is a very